Hello, everyone. Thanks for showing up for my talk. So before I go into the detail of the talk, I want to first thanks to all my collaborations during my PhD and my postdoc research. And this includes the two speakers later, Shibazaki-san and Masuzawa-san. Because I don't have time to go through everyone, but they all contribute to a part of this the research that I will show today. So today I will talk about the cycles of slow slip on non-planar subduction force and their implications on megathrust earthquake hazard. The megathrust earthquake is of particular interest to geophysics because most of the disaster earthquakes happen in subduction fault. So the oceanic plate and the continental plate, they convert under the tectonic loading, and they can release the strain energy in different types of slip mode. For example, the figure on the left is a conceptual model of the subduction interface. The larger asperity can release the energy in the mode of earthquake. So that means millimeter to meter per second fault slip. And there are also slow slip outside the earthquake asperities, which just slip only 1 to 2 orders of magnitude higher than the plate convergence rate. There are also low frequency earthquake and tremors, which appear on even smaller asperities. And even though the slow slip doesn't generate any seismic waves, they're still important to understand the faulting mechanisms in subduction zone. And they are also important when we analyze the seismic hazard and the tsunami generation. So far, most of the slow slip events are based on land-based networks, and we currently need more observation near the trend if we want to get a better picture of the slow slip, of the shallower slow slip and slow earthquakes. Slow slip events has been observed in a wide range of tectonic environments and phases of the earthquake cycles. So here there are many proposed models to explain the mechanics of slow slip and earthquake. So here I list some, and the figure on the right is a model for crustal fault based on St. Andrews fault, but it includes almost all of these key characteristics in the source of earthquake and the slow slip events. For example, the different tectonic loading and the depth variation of rheology from brittle frictional rupture to viscous flow. And from the lab experiments, the change of loading and the elastic stiffness of the rock can also generate different slip modes of either earthquake or aseismic slip. And the variation of temperature and pulp pressure with depth, also the velocity weakening to velocity strengthening changing at different fault slip can generate slow slip or significantly affect the slow slip. And also the geometric complexity, for example, seamount on the shallow part of subduction fault can give rise to or promotes the nucleation of either slow slip or shallower earthquakes. So this is a very complex, a very large complexity in the source of earthquake and slow slip. So this motivates us to study to look at some of the to use numerical method to study the physics of slow slip and earthquake. So this is an outline of this talk. I will first show the numerical models for slow slip cycles on non-planar subduction faults. I will use Cascadia and the Central Mexico subduction zones. And then I will show how can we use the slow slip cycle model to inform the dynamic rupture of the 2014 Guerrero earthquake. And at the very end, if I have time, I will introduce very quickly model that we are developing for a unified diffuse earthquake rupture. So most of the slow slipping events are observed in subduction zones. So here we compare the long-term repeated slow slip from 6 major subduction zones in the figure on the right. So we collect the source characteristic of magnitude and the recurrence interval or duration of the slow slip in each region, and we plot together with the fault slab dipping angle. We found that there seems a trend of increasing of magnitude or recurrence interval of slow slip with a smaller average dipping angle. So this motivates us to study the geometric. How does the geometric of slab can affect the source of slow slip in our model? This is how we build our numerical model. We use the quasi-dynamic relation between shear traction and the slip. We ignore the inertial effect, but we use radiation damping proportional to slip rate in this equation. We use the standard rate state friction and the aging law to constrain the fault strength involution on the fault. The figure on the right is the slab geometry we use for northern Cascadia. So we mesh the fault into small triangular elements at the depths between 30 to 50 kilometers, as shown by the contour. Here, we assume a nearly isostatic pulp load pressure at this depth, which is supported by the seismic imaging of high VPVS ratio at the depths of slow slip events. And we also use a lab experiment-based parameter for A minus B in rate state friction. And our fault will be driven by the long-term tectonic loading, and we can have this spontaneous appearance of slow slip that nucleates at the deep transitional depths and propagate very slowly up dip and then bilaterally migrate and then stop. So the movie on the left shows the fault slip during one episode of slow slip, and the figure on the right shows the long-term variation between different episodes. So we also calculate the surface displacement at different points. So you see the cumulative slip of each episode of slow slip. We compare. We want to see because in Cascadia and Japan, slow slip is always coming together with a non-volcanic tremor. So they called episodic tremor and slow slip sometimes. So here we want to compare how is the relation between tremor and the slow slip in Cascadia. So in the figure in the middle, we plot the cumulative moment and the moment rate in one slow slip episode, which are shown in black and red curve. And we also get the tremor activity catalog from Weck et al. 2009. And we found that at the onset of an increase of moment rate, there is like the increase, like a suddenly increase of the activity of non-volcanic tremor. And before, like 6 months before the ETS tremor, there is a small, like a very gradually increase of this tremor activity. And we found that this might be related to the gradually increase of this moment of this energy release in our modeled slow slip. We also compare the spatial, we also look at the detailed spatial variation of the fault slip during slow slip. So we defined like 3 stages in each episode based on the moment rate accumulation. So the preparation stage, you will see in the first row, the very gradually increase fault slip, and in the, we call it fast spreading stage, where the moment release dramatically increase. It's the slip rate and the rupture speed also both increase dramatically, and the healing will be left the fault depth will go back to log after the rupture. We compare our model result with geodetic inversion result. So on the left, we plot the average slow slip on the northern Cascadia, and the color shows that the maximum average accumulated slip appear in the center, which is about 2.4 centimeter. And this is agrees quite well with geodetic inversion in Schmidt and Gao 2010. So this shows that the maximum slip and the magnitude of our model, the slow slip, can capture the real inverted, the real geodetic inversion result. And the slip deficit in the center is less than 50%, which might be helpful for seismic hazard analysis in the future. We also compare 2 episodes slow slip in northern Cascadia and southern Cascadia. So the color is a fault slip, and the gray and the black areas are the synthetic and observational data. So we see the comparison of the surface displacement. It's quite good, and we also see this most of the northern slow slipping events are larger than the events in southern Cascadia. So the magnitude difference is shown here. But generally, they are in a good agreement with the observation. So we then investigate how does the change of this source parameter of this source characteristic in different episodes is related with our 3D curved fault model. So in this figure, we plot the shear traction variation along at the along strike at the 35 kilometer depth. And we also plot the dipping angle at the same depth in this red dashed line. And the black dashed line shows the local strike, which means how that the element change along strike, like change the tilting of the element. And we found, the diamond here represents, and the length of this bar shows the average of the maximum slip and the length of this rupture patch in the along at the same depth. And we found that the maximum or the larger slow slip is corresponding to the average shallower slab dipping. So, and it's also it also means that if you have a smaller local strike, it means that the slab is more flatter along strike. So it means that the flat fault will accumulate more energy during the inter SSE period, and also is promotes for larger or longer rupture distance during the SSE period. This we found this like this is consistent with what is found in Yu et al. 2018. They found the steeper bending of this fault will serve as a barrier in their co-seismic rupture in their earthquake cycles model. Yeah, so this is our story about Cascadia. Before I move on, I here just make an announcement that our the boundary element method is now free access on GitHub. So we have some active developer or user of this code. And if you are interested in using or helping with the development, just feel free to contact me. So we built the similar model for central Mexican subduction zone. We are interested in this region because you see here there are some historical magnitude 7 and above earthquake along the whole trench, but there is a 100 kilometer long segment that has no significant earthquake since 1911. So it's called Guerrero seismic gap. But in the deeper part, on the deeper fault in this area, there are these long-term slow slip events up to magnitude 7.6, repeated at every 4 to 5 years. The interesting story is that in 2014, just during the rupture of this slow slip events, there is a magnitude 7.2 thrust earthquake just nucleate at the edge of this slow slip rupture. So it's very interesting to investigate the relation. First, the physics of the long-term slow slip cycles here and the interaction between slow slip and the thrust earthquake. So that's we built. This is our numerical model for the slow slip only. So we use the same method and the 3D geometry in central Mexico. And we also see the good match between our model with surface GPS record. So the red and the black areas are the synthetic and the observation data here. Yeah, I will skip this part. Then because I want to focus on the influence from the slow slip in the earthquake rupture. So there is a newly published model about the fault heterogeneity in central Mexico. In the shallow part, they have this very smaller asperity or scatters of either low frequency earthquake, very low frequency earthquake and tremor. And in the deeper part, they have this slow slip rupture. So this like heterogeneity on the fault may reflect that the fault interface is very complex, and there and this model shows the proposed model for the slow slip event and the 2014 earthquake rupture. So the slow slip event will increase the Coulomb stress at the edge of this rupture. So finally trigger this co-seismic rupture. So this is a very interesting model, and we want to test with our numerical method. In this model, we try to link two different types of simulation. In the model, first we model the slow slip events with a boundary element method because it's more efficient if you ignore the inertial effect. And then we will use the residual stress on the fault from the slow slipping events to inform the initial setup of our dynamic model. The software we use is SSEs, which is very efficiently simulate dynamic rupture plus seismic wave propagation. So yeah, I will show this. The movie shows the variation of the ratio between shear to effect normal stress on variation during one slow slip episode. So the star is the hypocenter of this 2014 earthquake. You see during the rupture, I mean during the slow slip rupture, it will propagate or change the stress concentration along strike and push it towards to the hypocenter. So this is the figure on the right. It shows the vertical cross section, showing the variation of the ratio of this the traction ratio. And we just use the effect normal stress and the shear traction at the one-time step from our slow slip cycle model into the dynamic rupture model. So here is a dynamic rupture of our earthquake. You will see the appearance of co-seismic slip gradually nucleate from the hypocenter. We didn't use any additional shear stress to trigger the earthquake. We just take the initial stress from the slow slip model, and we choose a reasonable threshold of the static friction coefficient. So in that way, there will be the nucleation will appear here as the local maximum of the shear traction. And here the figure shows the cumulative slip of the earthquake. We also compare with some observational data. So the blue lines are the moment rate from seismic using a seismic station, and the red curve is our modeled moment rate. We have the shape of this two peak because there are two circular asperity on the fault, and we also compare with the surface deformation with the the regional GPS network. We kind of we kind of catch the first order characteristic of the rupture, but we seems overestimated the surface deformation. It's probably due to because the initial the initial effect normal stress is not change in our slow slip model, so it may be have a too large stress drop, lead to a too large stress drop in the dynamic rupture model. But the interesting thing about our model is that we for this except for this 2014 slow slip, there are three previous episodes of slow slip from 2002 to 2010, and we calculated the shear traction variation on the fault for these three previous episodes, which are shown in the black curves. So you will see the the stress concentration gradually increase at the depth of hypocenter, but the final one, like the 2014 one, is really the final events that push it really higher enough for the dashed line is a static friction coefficient we use in the model. So it will this event finally push it close to the rupture criteria and generate the dynamic rupture. So this is our story about the long-term deep slow slip events. We also interested in the shallower slow slip events because it affects the near trend rupture of co-seismic slip, and also can affect the tsunami generation. But in terms to the shallower slow slip events, is even more complicated because you could this is a structure of the shallower part of subduction interface from the paper of Sulfur and Wallace 2014-15. They kind of resolve the multiple space fault, and also the real curved fault interface, and the material on the fault is also complex because the temperature and the pore fluid status on the fault is very complex, and also the thermal pressurization, which change the pore fluid pressure and temperature, is also like candidate of fault weakening mechanism in the shallower to explain the shallower rupture of the earthquake. So to really capture the physics of the shallower slow slip, we think it might not be efficient to use this boundary element method. So this is a model we are currently developed in the group of LMU. We want to build a unified earthquake rupture model for the diffuse earthquake, which is in the framework of continuum mechanics and geodynamically geothermal compatible, and it can consider the real rheology of the materials, and is mesh independent. So we can use this adaptive mesh refinement to really capture the shear localization at the rupture front. So the movie here shows the spontaneously off-fault cracks during the shear sliding on the main fault in the middle. So we think that by using this numerical tool, we can really capture the geometric and rheology complexity in both earthquake and aseismic rupture in the future. Yeah, so I will stop here. So this is my conclusion and outreach. Thanks for listening, and I'm happy to take any questions.